Engineering. Today we are building a 1996 BP. We're building this guy for boost. So I'm going to go through what we've already done. We went and did a bunch of the nitty-gritty stuff so that we don't have to bore you to death with that. We've already measured everything, so we know for a fact this motor is going to go together, but I'm going to walk through what all we did. Step one, we got everything as clean as possible. So these blocks, the block was hot tanked, the head was hot tanked, everything degreased. We went ahead and masked it off and painted it. And we're going to go through this again, but we went through and cleaned all of the oil galleys out, and we're going to show you what we did there. Next thing we did is we mic'd our crank. We went through and checked all of the main and rod bearings, and we've set up our bearings in the block and torqued these all down and measured our bearing clearances. And we have recorded all of the clearances in our spreadsheet, and that will be going to the customer when we're done. So he has a record of every clearance. We have our piston to wall in there, we have crank end play, ring gap, etc. So we know that everything is going to fit perfectly. Alright, so let's go over some of the parts that we've got going here. This motor is being built for boost, and this is our tried and true recipe that we use. We use the Wiseco pistons, Manley rods, ACL race bearings, Leroy Engineering oil pump with the billet gear, that is like a requirement. Gates water pumps. This motor is getting stock springs, retainers, and valves put back in it. We're not raising the RPM, we're not doing aftermarket cams on this one. We still need to rebuild all of our lifters, so we'll take these apart, clean them, get them all purdy and new. What am I missing here? Oh, and ARP head studs and main studs. While we're on that subject, the machine work that we had done to this block, we had it line bored to get all the holes perfectly round for the hardened studs. We had it overboard. We're doing 83.5mm pistons, and we had the block resurfaced, so everything is true and square and brand new. We had the head decked, and all of the valve seats reground for the new valves. Alright, so we got to make sure that there is absolutely no dirt or metal shavings left from the machining operation in the block. So we're going to go through and follow every single one of the oil passages and make sure that's clean. There's two ways we do that. One good one is with a flashlight. You can shine a flashlight there and look down in the hole here and see the beam of light, and you can see that there's no obstructions in it. You can also shine the light that way and look down the hole and visually inspect that there's nothing in there. I typically, when I first get it back, we pressure wash it, and then I go through with compressed air and stick the compressed air nozzle down every single hole and make sure we blow all of the dirt out. You can also use a brush. This one's a little bit dirty, and if the stud was not there, send it down every single one of the oil galleys and clean it out. On the BP motor, the oil passage is the oil pump inlet is here, and it sends it through the block to the oil filter. It goes through the filter and back in and enters this main manifold inside the block. And we can see light coming through that manifold, maybe, all the way down. From this one main manifold, we have 5 runners that come up to each of the main bearings, and 4 runners that come up to each of the oil squirters. And we can look down and see a light down each of the oil squirter holes. And we want to make sure that there's absolutely no metal in the motor. We've had a couple of motors come in that were rebuilt and not cleaned properly, and a brand new motor self-destructed in a couple of miles because a piece of metal was left inside. And the motor was assembled correctly, but one little piece of metal got stuck somewhere, and we actually had one on a cylinder head. One piece of metal got stuck in this one little hole on this cam bearing, and everything else about the motor was fine. This one bearing stopped getting oil, completely melted, seized and grabbed the camshaft, timing belt spat off, and motor was done. So it does not take much. So the cleanliness is the utmost importance. It would be better, I would say, to get it perfectly clean and get one tolerance slightly out of spec than the other way around. So, but we're going to shoot to do neither. So this block's already been cleaned. We've already masked it all off. We painted it, and we've already measured all of our bearings. We'll go over how we went through and measured those. All right, so let's go over the bottom end real quick and what clearances should be. So, general rule of thumb is you want half a thou of oil clearance for every inch of bearing diameter. And that's the rule for using synthetic oils. Back in the day when people would use dyno oil, it was 1 thou per inch of bearing clearance. So if you were running a big block Chevy with a, just shy of a 3-inch journal, you'd be running about 3 thousandths of oil clearance. We have a just shy of 2-inch bearings here. So with our number, we're looking for, as the factory spec says, between 0.7 to 2-ish oil clearances. If you run bigger clearances, it's safer because there's more oil protecting your bearing, but you need a bigger pump oil pump at some point to keep up with the higher demand for it. If you run a tighter clearance, the engine will be more efficient. It does not have to pump as much oil, but the tiniest little speck of dirt going through there is going to wreck the motor. Lots of newer cars with these OW20 synthetic oils are running half thou oil clearances to get their fuel economy numbers where they need to be. And when we take them apart and build them for a race application, often we'll up those oil passages a lot. So in this case, we've already gone through and we can see here what our clearances were, and we've got 1.3 thou, 1.6, 1.7, 1.5, and 1. So there's our mains, and our rods are 1, 1.1, 1.2, and 1.1, which is pretty good. So you can use plastic gauge. You're not going to get that level of precision out of it, so what we do is we'll use our stare-at micrometer here, and we'll go through and we'll mic every single one of the bearings and record the number. And there is some variance. You see bearing 5, the reason that its oil clearance is slightly less is the journal is actually slightly larger on the 5th spot. And this is a used crank. It's got 240 some thousand miles on it. These are all still well within the factory spec. And all of our oil clearances are also within the factory spec. So to measure our oil clearance, we're going to accurately measure our journal diameter, and then we're going to set up our bore gauge and zero it off of our micrometer. I should have set this up beforehand, but so we'll set this up, we'll get our right size dial indicator in there, and then we're going to torque down our main caps with our bearings installed, and we'll stick this in there and find out exactly what our clearances are. And if something's not right, we're going to go back and figure out why. I usually measure everything twice. We're dealing with 1/10 of a thousandth here, so it's really good to be accurate with it. And you can mix bearings around. We can double check. If I get one that's just way out and I don't see why, if all of the crank journals are measuring the same size, I might move a bearing from one slot to another and check it again, make sure one of my bearings isn't bad. Make sure that when you're putting your bearings in, your caps are perfectly clean and you've wiped them down. A half a thou thick piece of dirt right there when you put your bearing down is going to give you an inaccurate number. So we make sure we clean these really, really, really good, and they're nice and dry and clean. Some people put lubricant on the backside of this. Now that is a bad idea. You do not want the bearing to rotate. There's no reason to have something between the two sides of this. You want that dry and you want it to stick. The reason the bearing does not spin when it's in there is if you push this down, you might be able to see this, but this bearing surface is actually higher than the deck height of this main cap. So when you torque it down, you're actually squeezing and pressing that bearing down into the cap, and the same is true on the block side. So when we torque this down, we're squishing those bearings, and that squishing is what's keeping them in place. How much you torque this down changes what your clearance is going to be. So it's important to have them torqued down, check that your holes are still round. So if we put in ARP studs and we're torquing it down tighter, we usually then have to go through and remachine the hole through the center of the block to get a perfect round and inline hole again. Alright, so that'll be all measured, and we're going to repeat the exact same process with the rods. So we're going to put our rod together, torque it down with the bearings inside, check our crank, check our rod diameter, record the number, and make sure that we're within the spec for what we're building. Alright, important note, we had this block taken to a machine shop, and we did everything correctly. We gave him the pistons, he had the block, I gave him all of the specs I wanted, I told him my piston to wall I wanted, I told him the bearing clearance I wanted, and he machined it. Now a lot of people do all of that and then just throw the engine together without remeasuring everything. Why would you remeasure it if the machinist that you trust just did it? We are all humans and we all make mistakes. Our machinist is phenomenal. He does tons of high horsepower drag motors, he's the best in the business. He's still a human, he still can make mistakes. And it's way easier to catch him before you put it together than to put a whole engine together and it blow up because you didn't check something. We had one motor come back where one of the main caps didn't get line bored for some reason. It wasn't torqued down correctly. Minor issue, he happily fixed it for free. No harm, no foul. You gotta check everything. I hear so many horror stories on the internet of people throwing it together and missing something. We've gotten the wrong bearings shipped to us before, completely by mistake. I had a set of rings once that were packaged with the correct part number on it. And then we looked on the side of the package and it was the wrong part number. And after measuring them, they were the wrong rings. And if we had just thrown them in without measuring, we would have had about a 40 thousandths ring gap. Went back to Wiseco, no harm, no foul. They swapped them out for the correct rings, we went on our way. You gotta check. We're all humans, we all make mistakes. So that's the reason that we spend basically a full day before we build an engine checking every single part on it. And most of the time, yep, all checks out good, we're happy we put the motor together, but that one time you catch something, you go, oh, I'm so thankful that I checked everything. So if you're going to be building a motor yourself, it doesn't matter who does the machine work, invest in a quality set of tools. It is going to run you about $1,000 to get all of the correct measuring equipment that you need to do it correctly. Or you can do the YouTube cheater method and just poke and hope, and hopefully it runs long enough to get your video out. But if you want it to last, you got to go through and measure everything and make sure it's correct. Alright, so we're putting our oil galley plugs back in. There's two plugs here you have to remove to clean the block. And I had one and I didn't throw it. The only way to get them out is to drill a hole through the first one. You can send a long rod down and pop the back one out, then go around the other direction and pop the first one out. So you wind up losing at least one of these. But you can buy them new from Mazda, nice tight fit. And it's got a chamfer on one side, and that chamfer matches chamfer on the inside of the block right there. And you want to pound this in until it bottoms out, and it's going to give you a nice solid seat, and you'll see shavings come off of this as it press fits back in. So, again, I use a hammer to get it flush, and then a socket to drive it all the way in. You'll hear a tone change. There. Yeah. We're flush. Very important to remember to do that before you put it together, because the oil pump covers it and you cannot put it in after the fact. So you'll be hurting if you forget it. Alright, piston to wall clearance. So, as we know, a piston is not a cylinder when it's at room temperature. Because there's so much more mass at the top of the piston and the bottom of it is essentially hollow, as it heats up and expands, it's going to change shape. And the more mass at the top is actually going to cause it to expand more. So in the cold state, it's actually a cone. And it's about 5 to 6 thousandths narrower at the top than the bottom. We want to make sure that when it goes in the hole, we have the right amount of gap between the piston and the wall. So when you buy a quality piston, at least, you'll get a spec sheet that tells you where you're on this piston skirt it wants you to take your measurement from, and then it also will give you a recommended clearance. So we've done that. We've measured, and you can give this sheet to your machinist when you go in. We've measured 1.3 inches down. We've got a recording there, and then we've measured with our bore gauge the block all the way around and made sure that we have the clearance that we want. Too tight, and the piston will heat up and get stuck in the bore. Too big, and it'll work, but you'll hear piston slap, they call it, where the piston's dancing around up and down on the way up and down. Now, if you were to measure it, most pistons, including these Wiseco's, have what's called an offset pin. The wrist pin is not actually in the middle of the piston, it's just a hair over to one side, and the idea is that it'll rock over to one side and then just stay there, and it reduces the noise. We have had a couple of motors. The Supertex have been the worst offender for us so far, of just being really, really noisy pistons. They don't expand fast enough, and so during those cold startups, it just rattles and it sounds very terrible. The Wiseco's with these nice skirt coatings have been phenomenal. We use Wiseco's unless the customer specifically requests that we don't. We use Wiseco's on everything. So, next up, the only thing we haven't measured and done yet is we have not ground our piston rings to size. But we're going to go ahead and install the crankshaft first and check our end play, and then we'll go back and we'll cut all of our rings, and then we'll be able to slot our pistons in. The other thing we've already done is we've already gone through and weight matched all of our pistons and rods, and I have the numbers of what they weigh and what hole they go into written on the bottom, and again that's recorded in our spreadsheet. Since it is a flat plane crank, the crank is balanced to neutral, and we simply have to get all four of our piston and rod combos to weigh exactly the same. And you can get really close just by mixing and matching rods and pistons. If we look at what we had to do here. So our pistons varied by less than 0.2 grams. Our rods varied by quite a bit more. But you got to remember that 1 and 4 are on the same stroke, so they add up together. And 2 and 3 are on the same stroke and add up together. So once I've weight matched each of my sets, I matched pairs, and we were able to get the entire rotating assembly to within 0.2 grams of perfectly balanced without having to grind anything, which is not bad. Alright, so we're going to get our oil squirters installed. Now the way these work is there's a banjo bolt with a ball bearing and a spring inside. And I do not know the pressure rating, but at some pressure they're allowed to open. So below a certain pressure level, like when you're idling and once the oil is hot, these guys are closed and not squirting the pistons. When the pressure builds up, it pushes that ball out of the way and lets some of the pressure flow through and squirt up in here. So we want to check all of these. It would be very bad if one of these was stuck open, because that would be just an oil leak. So we check all of these the old-fashioned way. Make sure that we have no dirt in there and air flows through just fine. And we check all of the bearings to make sure the springs move and none of them are stuck in the down position. Now, someone brought up at some point, depending on what piston you go with, they can interfere with the oil squirters. I happen to know these ones don't, but we've done some high compression builds and stuff where the pistons for strength have a casting that goes from here to the wall, and it's right in line with the oil squirter. When we do those, we have had to make our own oil squirters, and it's easy to do. So we'll put one of the pistons in. We'll see where it lines up. We'll heat this up and basically make a jog in this where it slides over and then comes back up to the direction and clean out the hole again to get them to bypass. Some people do delete the squirters. The purpose of this is to throw oil up to the bottom of the piston for cooling. If you're not having a particularly hot combustion charge, it is a viable option to delete these. You will pick up a little bit of oil pressure, just depends on what you're doing. If you're doing a boosted application, I recommend keeping them in there because you're going to have really high cylinder temps and it doesn't hurt anything. So we're going to get these installed now. So I put a little bit of Loctite on these threads just because I'm paranoid about them coming out. This is not in the factory manual, but in my mind everything either needs a lock nut or block tight. So we're going to go ahead and drop these into the block. And if you have a friend with really small hands, this is when you call them over. Okay, so we're going to get all these in, we're going to torque them down. And we're going to start our torque sheet that we do with each motor at this point. And we're going to record what we torque every bolt to. The factory spec on these, I think, is like 14 foot-pounds. Put them at about 20. Because 14 seems not near enough in my mind. Okay.